Sure, let's get started. So, welcome back. I hope you had a nice enough holiday. Please remember that this semester 2 is much, much shorter than semester 1. Okay, so please don't think, we had semester 1, it went on for so long, we're going to have the same for this semester. That is not the case. So we'll see here, where are we? Okay, over here, 20th of July. We have 1, 2, 3 weeks, and then the class test. So 3 weeks, and then class test 3. Then we have another 1, 2, 3, 4 weeks, class test 4. And then 1, 2, 3 weeks, and then class test 5. Okay, it goes very, very quickly. So please prepare yourselves for the test. So as soon as I give you like the scope for the class test 3, that day you must start preparing for class test 3, right? It's 3 weeks. I mean, that goes by very, very quickly. Okay, and then now class test 5. So we should have class test 3 and 4. That will definitely happen. I also want to include a class test 5 that covers everything for the exam. Okay, because this is the first year where the first years are having full exams. So we're not too sure how that's going to go. So I'm wanting to include a class test 5 for 50 marks. That will be the same scope as your final exam, but just half as much. So in the final exam, if the question is out of 2 marks, I copy paste the question and make it out of 1 mark. Right? So you get an idea of what to expect. So over here, probably around 21 October, lectures will then end for the year. Okay, so October, mid-October, maybe somewhere around here, then we have revision. That's it for the year. Okay, so probably here, mid-October, we'll be done with lectures for the year. Then the following week, we have the revision. Then you have your final class test. And then exams will start for all of your modules. Remember, for the engineering, those are semester exams, okay, like you had before. But for the maths and the physics, those are year-long exams. They cover everything for the whole year. Okay, so right from lecture 1, where I said this is a set, right up to the final lecture where we go through the net change theorem, all of that is in the exam. Okay, and that will count 50% to your year mark. So all of the quizzes, tutorials, all of that stuff, that will be 50%, and then your final exam, 50%. Okay. In order to fully pass the year, you need to pass everything. So all of your engineering modules, maths and the physics. If you fail anything or you have failed one of the engineering modules, you are adding another year to your degree. Okay, because you have to repeat the whole year, pay the whole year, to catch up with that one module. Okay. Now, to make it into the MATH161 for next year, you need a minimum of 40%. Okay, so if you get 40%, you can then go into MATH161 and write that exam. However, you will need to repeat MATH131. That's the mainstream. So all of the stuff that we've done over this full year, you then repeat in semester 1. So the whole year's work, but in semester 1. That will then catch you up to do the semester 2 work. Okay. The same thing goes for the physics. Everyone clear on that? Okay. So if you fail any of the engineering modules, you're adding a year already. If you fail the maths or the physics, again, you're adding another year as well. Okay. And if you fail, say, the engineering modules and the physics, you might even be adding 2 years. Okay. To catch up, because you can't do like 8 modules in one semester, right? You need to separate it a bit. Okay, everyone clear? Okay. So let's just go through the test dates. These aren't finalized, but somewhere within that week, we should be having the test. So maybe it's the Monday, maybe it's the Friday, but expect somewhere in that week. If there are any clashes with physics, do you have your test dates for physics? No. Okay, so just when you do get them, just double check with this. If there is a clash on the same day, we can make a plan. Otherwise, you're writing 2 tests on the same day, but I can't do so much with that. Okay, class test 3. This is probably going to be on the 12th of August. Okay, again, keep in mind, this is the 20th of July, 12th of August, very close. Okay, class test 4. This will probably be on the 16th of September. So about a month between those two. And then class test 5. This will be on the 28th of October. It will give you two and a bit weeks from when our lectures end to when you write this class test 5. Yeah. Now the scope for these, class test 3. This will be on optimization. That's what we're covering this week. Anti-derivatives, that will be stuff we're starting next week. And the area problem, that will be the third week. And then after that, you're out the test. Again, just to make it a little bit easier for you, this will be only on polynomials. Okay, you don't know what that means, but just make a note, it's only polynomials. Okay. So that's for the class test 3. Class test 4. Okay, this will be on definite integrals. Okay, definite integral properties. Okay, this is just all proofs. Okay, so the first part, definite integrals, that's going to be calculations. Definite integral properties, that's all proofs. Okay. And then the last thing, FTC. Okay, don't worry about the name, we'll get to that later. Just make a note there, FTC 1 and 2, proofs and applications. Okay, and by applications, that's just calculating stuff. Okay, so later on in the semester, after this chapter on optimizations, this rest over there, antiderivatives going down, that will be on integral calculus. So all of semester 1, we did differential calculus. And then after this, we're going to move to integral calculus, all of that stuff there. And then next year for the MATH161, that will only be on integral calculus. So it carries over like that. And then just a note here for class test 4, about half the test will be calculating. So definite integrals and that FTC applications, that's just calculating things. Then the other half will be on the proofs. So definite integral proofs and FTC 1 and 2 proofs. Okay, it'll be about half-half. Okay, and then for the final exam, it will be around 1/4 proofs and then 75% calculations. So calculations, right from the beginning, find the inverse function, that type of thing, all the way up to definite integrals, all of that calculation stuff, and then the rest will be proofs. So, right, remember way back when we did the set proofs, that stuff, proving something is continuous, proving something is differentiable, proving FTC 1 or 2, proving definite integral properties. It's a mix of all of that. Okay, that'll be 25%. Any questions for that? Oh, good. Okay, and then the class test 5. This will just be whatever the exam scope ends up being. Okay. So I'll put up the exam scope so you can have a look through that. Some sections will be thrown out, not so important, but the full exam scope will be given, and then the stuff that's not there, you can just completely ignore. Okay. For example, linear approximations. If that doesn't show up in the exam scope, you will not see it at all in any form. Okay, it's completely thrown out. But if it is in the exam scope, it will be in class test 5, and it will be in your exam as either a calculation or a proof. Okay. If it is a proof, I will put a little star there to say proof. You know how to learn proofs and stuff. Okay. Also on the proofs, some of them will be unseen. Not a lot. A couple of them will be unseen. Maybe 5 marks out of the 25, maximum 10 marks out of the 25. That will be unseen. Now, it won't be completely unseen. It will be related to something that we have done, but you would have not seen it in class or tutorials, anything. Okay. It's to test, can you actually go further than the classwork? Okay, everyone understood that? All good? Okay. So that's it for the admin stuff. Let's go on to optimization. Also, those that didn't read the email, there's no tutorial this week. So that tutorial time is free. You do whatever you want. But then next week, the tutorial start as normal with the tutorial assignment. You do in your little groups, the quiz, and the written stuff. So this, I think it's the Wednesday, that morning double period, that's free for you. That's not the same for the other modules. Please check with them. Their tutorials might start this week. Okay, please check. Okay, let's start. Optimization. Okay, so you should have done some form of optimization in grade 12, finding the min, finding the max. Here we're going to do similar problems, but they're going to be a bit more technical. So here we're going to find minimum and maximum subject to certain constraints. So it's not just, d by dx set it to 0. There's a few extra things that you need to consider. A little bit more difficult than metric, but not too much. Okay, so given a function f, we would like to find the maximum or minimum of the function subject to some given constraints. So these constraints that we're adding on, that might be a new thing that you haven't seen in high school. Yeah, but the whole idea is to find the maximum or the minimum of the function. So depending on the problem, you're either looking for the maximum or the minimum. For example, if the goal is to look at the profits being made by a company, obviously we want to try to maximize the profits. Okay. On the other hand, for engineering, if you want to minimize the materials of something, you want to minimize the cost or minimize the time or the materials. So it depends on the problem, whether we want the maximum or the minimum, but the method is exactly the same for both cases. Okay, so let's have a look at a little picture here. Okay, maybe we have some function like this, f. Over here, we can see that this is the maximum point of the function. So over whatever interval we're looking at, let's say the whole interval, whole axis there, that point at the top there, that will be the maximum. Okay. On the other hand, that point there on the right there, that will be the minimum. Right? That's pretty obvious. Okay. However, when we include constraints to the problem, it gets a bit more difficult. Let's say that we can't look at all of the x values. We are only looking at a certain window of x values. So if we are outside that window, that's not a valid solution. We're only looking at solutions within a certain range. So let's say we have something like this instead. Okay, so similar sorts of function, but now, wait. Okay, but now we're only looking at this interval from A to B. Okay. Now it makes things a little bit more difficult because we're not only interested in these points over here, we are also interested in these endpoints at A and at B. So here we have two more points that we need to consider. Okay, why is that? Well, because on the endpoints, the function could have a value larger than those white dots in between. Okay, or on the endpoints, the function could be lower than at those points in the middle. For example, we could have something like this. Yeah, something like that. We see that at the top here, that's the maximum. Over here is the minimum, and the endpoints are somewhere in between like that. Okay, so that's similar to this picture over here. But if we look at this next picture, okay, something like that, we see that we have our normal maximum over here. Let's put the white dot there. But the endpoint, the minimum point is no longer this turning point over here. The minimum is actually at this endpoint over here. So there, let's put those in pink like we had before. Okay, so in the first case, in the top right over there, we have the maximum and the minimum occurred at the turning points, okay, like you saw before. But over here in this bottom picture, we see that the maximum is still at a turning point, but the minimum is no longer at a turning point. You see that? Yeah, the minimum is at an endpoint. So when we're looking for the minimum and the maximum, we can't just be looking at the turning points. Okay, it might be at a turning point, like in that top picture. However, it might also be at an endpoint. Okay, does that make sense? Okay. So note, given a constraint on x, e.g., let's say it has to lie in an interval, the min and max could occur at the turning points, or at the endpoints. Okay. So in high school, you would have taken your function, set the derivative equal to 0, solve for x, and that would be your min or your max. However, now if we include the endpoints there, like the x must be between a and b, you need to check those as well. Okay. So whatever turning points you get, you add that to a list. You add the endpoints to a list. And then after all of that, you then check for the minimum and the maximum. Okay. Does that make sense? Okay. Now, there's some terminology for this. Okay, the min and max that occur at the turning points are called the local min and the local max. Okay. Because it's only the maximum or the minimum around that turning point. For example, over here, maybe we had some turning point there. This is the local maximum, because if you look around the turning point, it's the largest point there. Over here, this isn't a turning point, but it's still a minimum. So we give it the other name of global minimum. So out of all of them, what is the global minimum? It might be a turning point, it might not be. Okay. But over the whole interval, the lowest possible point, that is the global minimum or global maximum. And then if it's a turning point, that is the local minimum or local maximum. Okay. It's just special names we give to those. So the min and max out of all the points. So remember, this first bit is only for the turning points. This is now the min and the max out of all of the points. Are called the global min, because you're looking at all of it globally. And the global max. Yeah. So that's the terminology that we're going to use. If you're looking in the other textbooks or online, there's other names for this. So local min, that also has the name relative min. Okay, we're not going to be using that name, but if you do see it, it means the same thing. So local max, relative max, again, same thing. Yeah, it's just different names. And then for global min and global max, sometimes it's called the absolute min and the absolute max. Again, different names, same thing. Okay, and then the global max. Another name is the absolute max. And again, this is just different names. Yeah. Any questions so far? All good. Okay. The next bit of terminology is defining what a critical point is. And you should have covered that in high school. Okay, but I'll just write it out again for you. So a critical point is a value of x such that f prime of x is equal to 0. And this is the important bit. Please don't forget this other part. Or f prime is undefined. Okay, so lots of terminology for the same thing. If we only look at that first part, f prime is equal to 0, that's just a renaming of a turning point, right? So a turning point is where f prime is 0. Okay, so why do we call it critical point? Well, we give it another name, critical point, because of the second condition here, f prime being undefined. Okay, now, why do we add that? We know turning points can be the max or the min, or local max, local min. Why do we include that? So just to think about this, what happens if we have the following situation? Okay, we've got a continuous function, like that absolute function type thing. So we've got something like this. At that point in the middle there, that is a maximum, right? But we're never going to find that point using f prime equals 0. Why? Yeah. So it's a maximum. We know that there. But this first condition, f prime equals 0, why does that not work? Sorry? That's not differentiable. Yeah, nice. You can get some points for that. You get extra 2 points for those. What's that? 20%. So someone's at 20% already. We haven't even had the assessment. Yeah, it's not differentiable. So that first condition doesn't work. So the reason we include that second condition is because of these cases like this. If the function is not differentiable, it still has a min or a max. So how do we find the possible min or max? We check where the derivative is undefined. Okay, so think about these cases over here. Now, for our examples, f is going to be differentiable, right? But sometimes you might get a function like that, and then you need to check that second condition as well. Okay, but most of the time, we'll get away with just doing that first condition. Okay, but please keep in mind there are 2 conditions for a critical point and 1 condition for a turning point. Okay, that makes the difference between the 2. So if the class test 1 has a question, explain the difference between turning points and critical points, you need to explain something like that in that cloud. Okay. Any questions? All clear. So if we're only looking at that first condition, it's a turning point. If we're looking at that first condition or the second condition, it's a critical point. Right. Any questions before we get to the examples? Okay, let's have a look at the examples. Okay, so for these first few, I'm going to list out steps that you should be following. Now, it's up to you if you follow the steps or not, right? It's just a suggestion. But there's about 5 steps that if you follow them, you will always get the right answer. Okay. Now, if you want to combine the steps, right, you're really smart, you can do steps 1 and 2 in the same step. That's perfectly fine. You're not going to lose any marks. But if you can show me these 5 steps, you're not going to get lost halfway through. Okay. So let's go through example number 1. And again, I'll put up step 1, step 2, step 3, so you can follow along. Okay, a farmer has 1,200 meters of fencing. And wants to fence off a rectangular area that borders a straight river. Okay. He doesn't need fencing along the river. So we're going to have some river. We're going to fence off a rectangular area. but along that river side, there's no fence. Okay, so he doesn't need fencing along the river. Okay. What are the dimensions of the rectangle that give a maximum area? So all of the problems in the tutorial, the quizzes, the test will be something like this. Okay, some word problem. We need to interpret the word problem, get some equations, and then finally answer whatever question is at the end. Okay, so step 1 is to draw some pictures. Again, these steps are just suggestions. If you can answer the question without drawing pictures, if you get it right, you get it right. I'm not too worried about that. But if you do include the pictures and you get the final answer wrong, I can give you some part marks for the pictures. Okay, so just keep that in mind. You know, these 5 steps, they can give you your part marks if you mess up towards the end. Okay, so what exactly do we want here? We have some river and we want to set up this rectangular field, okay, over there, such that the area is a maximum. Okay, and one of the sides is missing because we don't need fencing along the river. So let's draw a picture. So we've got a river and we have our fencing like that. Very simple. And notice we don't draw anything at the bottom because there's no fencing next to the river. And we are interested in maximizing this area that's being shaded in. Okay, very easy. Step 1, you get a mark, right? Something like that. Okay, step 2, add some labels. Okay, so in the question, there's no variables given. I don't say X or Y or anything like that. That is all up to you. So if we're actually going to set up a function and do the derivative, we need some variables. Okay, now it's entirely up to you what you call what. Let's say that this vertical part there is Y. Makes sense. Let's say the horizontal part is X. Makes sense. So we're going to label it like that. So we've got our river. In the test, please do not draw it twice. You only need to do it once. Okay, we've got that. And we've got X, we've got Y, and this other side will also be Y. Okay, so we have something to work with now. Okay, step 3 is to define the function that we want to maximize. In the question, it said the area, so we want to maximize that. We also want to define the constraints. Okay, like we said at the beginning, it's not just some function that we have the derivative of. There's some constraints to the problem. For example, there's some minimum value, some maximum value we can only look at. Or in this case, the total fence, the total fence bit there is 1,200. That's the maximum amount of fence we can have. You can't form a rectangle with more fence than we actually have. Yeah, so this is a constraint. You can't go more than 1,200 meters. Okay, so step 3, define the function and define the constraints. And you need to be able to identify the constraints. So the question won't say, here's the function, here's the constraints. You need to figure that out from what's given. So step 3, define the function to optimize. So here I say optimize because it might be minimized, it might be maximized. It depends on the problem. In this case, we want to maximize the area. But in general, we can just say the function that we want to optimize. And we also want to define the constraints. Right, there's some limits on this, x and y. They can't be as big as we want. There's a fixed amount of fencing we have to work with. Okay. So again, what do we want to optimize? We want to maximize the area. Okay, so if we want to maximize the area, well, that gives us our function. Let's call it A. What's the area going to be? Just x times y. Easy. Okay, and what about the constraints? Careful. X plus 2y. Good. So constraints. X plus 2y, that is what is being constrained. Okay, the total perimeter. We cannot go more than 1,200. Okay, so we have everything listed out nicely. What we want to do is maximize that A function. Now notice on the right side of A, we have two variables, x and y. That's going to cause us some problems because when we do the derivative, we need d by dx, right? Not y. We don't want to include that. So we want to eliminate y and write this A function as a single variable function. So we want to eliminate y to get A as a single variable function. I.e. A of just x. Because if we have A of just x, we can do A prime, solve for x, we got our answer. Okay, so how do we do that? Well, just looking at the function by itself, there's no way to do that. But we have a constraint that relates the two. Notice x and y are related by that constraint. So we can solve for y in terms of x, substitute it back, and then we get our single variable function. Okay, so the idea, use the constraint to solve for y. Sub back into A. And finally get A of x. Okay. So let's do that. So we have A is equal to x times y. That's just from the beginning there. And here we want to solve for y. So x plus 2y is equal to 1,200. We want to solve for y. So let's do that. Okay, and then we can divide by 2. And then, like we said, sub back into A, and that will give us just A of x. We end up with that. Now, to find the min or the max, we just go back to what we said before. We need to find these critical points, right? But A is differentiable, so we don't have to worry about that f prime being undefined. We can ignore that. So finding the critical points is now just equivalent to finding the turning points. Okay, there's no issue with that other condition. Okay, so finding the critical points is equivalent to finding the turning points. You can just take the derivative. Now, either you can take the derivative directly, but then we have to use the product rule. There's a product, x and that other stuff. Okay? Or you can multiply it out and then do the derivative. Okay, whatever you're comfortable with, you do that. Let's multiply it out. So A of x is equal to, that first bit will be half of 1,200. So 600 x. Okay, minus, and then half x and x, half x squared. Okay, so I multiplied it out, and then I'm going to do the derivative. If you want to do the derivative right away, that's fine, you do that. Okay, a prime. So that will just be 600 minus 2 just comes down, easy stuff, x. And we want this to be equal to 0. Right, that's how we find turning points. Very easy, x equals 600. Okay, but we're not done yet. Let's go back to the question. What are the dimensions of the rectangle? Here, x equals 600, we got the width, but the dimensions is the width and the height. You can't just give half an answer. Okay, so if x equals 600, then y must be 300. Okay, and at the end, you can put your units, meters there. Okay, so again, please do not give half answers. If the question says find the dimensions, a rectangle has a width and a height. If you just stop at x, you're getting half marks for the final answer because you're leaving out the height. Okay. Any questions for this one? Oh, good. I think we have time for one more. Okay, yeah, now let's do this next one. Number 2. Okay, a closed cylindrical can. Just while I'm writing this, from marking your previous tests with that rate of change, many of you do not know what a cylinder is. Okay, please put a very big star over here and say you learn the area and the volume of those basic shapes. Okay, so I said that before with that rates of change, you know, the volume of a cone, cylinder, sphere, all of that stuff. Same thing here. Okay, so cylinder, the surface area, volume, cone, surface area, volume, all of that stuff applies as well here. Okay, so a closed cylindrical can, and I'll put a little star there. Please make a note. Closed cylindrical can is to be made to hold 1 liter of oil. Right, you know those little oil cans. Okay, find the dimensions. And again, don't give half answers. When it says dimensions, if it's a cylinder, cylinders have a radius and a height. You need to provide both. Find the dimensions of the can. Such that the cost to manufacture is minimized. So cost to manufacture is minimized. So that's our goal, is to find some cost function for this, minimize that, and get our radius and height. Okay, so let's go through the steps. Step 1. Let's draw some pictures. So we know it's a closed cylinder, so it's going to look something like this. Okay, closed cylinder. Emphasis on the closed part, right? You don't want a leaky can. So it must have the sides of the cylinder, the top of the cylinder, and the bottom. Okay, all included. Okay, so top, bottom, and all of the sides, that's fully included for the cylinder. Okay, so step 1 done. Let's go to step 2. Add some labels. Okay, so I'm just redrawing our cylinder. The cylinder is going to have some radius, so let's put that in. And it's going to have some height. Let's put that in. Okay, again, you can call it X and Y, you can call it whatever you like, but that's going to be up to you, right? You need to know how to label these. Okay, now what we want to do is minimize the cost of manufacturing this can. So to manufacture it, we're going to need some amount of metal, right, to make the can. So if we minimize the surface area of this can, that's equivalent to minimizing the amount of metal we use, right? Because the surface area, that's going to be made of metal. If we minimize the amount of metal being used, that will then minimize the cost. So it's not a direct one-to-one. You have to do a little bit of thinking. So to minimize the cost, we want to minimize the surface area. So minimize the surface area. That's equivalent to minimizing the amounts of metal used, because that makes up the surface area. And if we minimize the amounts of metal used, obviously it's going to be cheaper. And this is what we want here. Right? We want minimum cost. So the goal is shifted from minimizing the cost to minimizing the surface area, but they are equivalent. Okay, so let's figure out a function for the area. So step 3. Define the function to be optimized. In this case, minimized. We want to minimize the surface area. And define the constraints. Right? We can't take any value of radius and height. There's some constraints involved. Okay, so the function, let's call it A for area, or you can call it S for surface area. It's up to you. We go back to our picture. Remember, we said all of this was included, the top, the bottom, and the sides. So the surface area is not just the can label sort of thing. It's the top, the bottom, and the can going around. So the area will be the top and the bottom. Those are just circles. We have 2 of them. And the side of the can, that's just 2 pi RH. Okay. So we've got our area. Notice it is in terms of the radius and the height. 2 variables. We don't want 2 variables. We want 1 variable. So we need to eliminate something. How do we eliminate something? We can use a constraint. So that's the function. What will the constraint be if we go back to the word problem? The volume, yeah. So it's not explicitly said the constraint is the volume, but we know it must be the volume because it has to hold 1 liter. Okay. So again, it's not directly, this is the constraint. You need to do a little bit of thinking. So if the volume must be 1 liter, that is a constraint. It must be this. Okay, so the volume, pi r squared h, must be 1 liter, or 1,000 centimeters cubed. Okay, now we can use this constraint to eliminate one of the variables. So a little bit of rearranging here. Let's get rid of the h. Okay, so we have h in terms of r. If we substitute that back, it becomes a function of just 1 variable. So the area, only in terms of the radius now, not in terms of the height, is equal to 2 pi r squared plus, and then 2 pi rh, but we substitute. Okay, so we have that. Now for homework, you're going to do this the other way around. Instead of eliminating h and getting this equation, you're going to eliminate the radius. You're going to get a different equation, but you should get the same answer. So homework, repeat the same, but eliminate the radius. Okay. So now you'll get area in terms of the height. Okay, so right at the end, you should get the same answer. Please check that. Okay, so we've got this. Again, like before, this is fully differentiable. So we don't have to worry about any f primes being undefined, which means the critical points are just the turning points. We don't have to worry about any undefined behavior. So let's find the turning points. Okay, so it's just normal a prime. This will be a minus. And we want that to be 0 so that we can find the turning points, or equivalently the critical points. Okay, we've got r squared at the bottom there. Fractions are a bit messy to work with, so let's clear the denominator. Okay, now it's just straightforward, solve for the radius. So we take the 2000 over, divided by 4 pi. That'll be 500 over pi. And then we just take the cube roots. Okay, so that gives us our radius in centimeters, like we had before. And if we have the radius, we can substitute back into here. Over there, you put the radius, and then you can get the height. So I'll let you do that calculation. Very easy. We just end up with twice that. Okay, so we got the radius, and we got the height. So this last bit here, you just substitute into the constraints that we have there. Right. Any questions for this one? Okay. Pretty simple. So remember, what's it? Wednesday, no tutorial. You do your own thing. Then the Thursday, we have the lecture in S6. Okay, last semester it was S3, now it's S6. Okay, please note the change. So we'll go through a few more slightly more difficult problems, and then I'll go over what will be in the quiz. Right, any questions? You're all good. Okay, so I'll see you on the Thursday.